This is a clarification basin. It's still part of secondary. So water in the aeration basins is going to come over here all brown and full of microorganisms in the very innermost ring of this basin. It's going to flow out through the trapdoors you see here, and it's going to hit this next ring. Now that's going to cause the water to stop moving, and then the heaviest material, the microorganisms, are going to start to settle to the bottom. On the bottom, notice there's this big boom arm, and it's got what looks like vacuum nozzles mounted on it. So it's going to sweep around the bottom of the tank, siphoning up all the microorganisms as they settle. The water slips underneath the skirt here and comes up relatively clear on the outside of the tank, where it's captured in the outermost weir and can head off to the tertiary filters. So clarification is a detention time of 4 to 5 hours. And we recycle the bacteria that settle back to the aeration basins. So we have a self-sustaining population. They're hungry and ready to go again. In fact, they're so prolific, a small percentage is culled out and joins the solids in the anaerobic digester. The water then is ready to go on to the tertiary filters. It's collected at the surface where it's cleanest. Now this particular tank is offline at the moment. So if we don't need treatment capacity, we shut things down to save money, and obviously we need the redundancy, which allows us to rotate everything for maintenance and cleaning. In the meantime, we have operational basins just over here, which we'll go and take a look at and compare. Operates the same way, looks just the same, but this one's full. This clarification basin is operating, and you can see, like we saw over there, the middle is where the water's coming in from the aeration basins. It's very brown and full of microorganisms. As they settle to the bottom, they're removed, and water is coming underneath to this side of the tank, where it's really much clearer, and it's captured in this outermost weir, and this water is now going on to the filters. So our next stop will be to go and check out the tertiary filters. Okay, here we are on the top of our tertiary filter building. We're going to lift the water up to the top of this building, send it across the roof, and then distribute it into each of these tanks you see here. So water enters the tank where it's evenly distributed across the surface. It's just allowed to overflow its weir and trickle down. And what it's headed for is a 4-foot bed of this anthracite coal. So all the little places in between the bits of coal are going to act as a fairly fine filter to remove the finest suspended solids, the big clumps of stuff that didn't quite settle in the clarifiers, as well as some potential pathogens. And it's really just minutes to work down through the bed and collect in a filter box at the bottom, and then off to disinfection. Now, over the course of about 4 days, the filter gets pretty plugged up, and water can't make it through quickly, so it starts to back up. So you see where there's a kind of a dirty bathtub ring. When the water reaches that level, we shut off flow to the tank. We allow the tank to slowly drain, and then we scour the coal bed, clean it, and then it's ready to go again. Once the water travels down through the bed, it's captured in the filter box, heads over to disinfection. Our UV light channels is our next stop. This is our ultraviolet disinfection system. It replaces the conventional chlorine disinfection used in most sewage treatment plants, as well as drinking water facilities. And it's really very simple. We have 3 channels set up, and each channel has 9 of these ballast arms. And the ballast arm will be lowered down into the channel, and water will flow in between rows of this ultraviolet light. UV channels have 9 arms per bank and 4 banks per channel. Now this is a very short wavelength, high energy light that's powerful enough to literally rattle apart and unravel the DNA or RNA of bacteria and viruses. And without DNA, of course, there can be no reproduction, there can be no cellular metabolism, so we have destroyed the organism. And it's literally a 2-second exposure time, that's all that required. So we determine how many channels we run and how many banks within the channel based on our flow at any given time. So from here, the water is disinfected, it's safe for human contact, and it's ready to leave the facility. Finishing our story of sewage treatment at the UV chambers is a little anticlimactic because you can't see how clean the water is. So here we are at our fabulous fountain showcasing the final effluent, the sewage that has been fully treated. A mere 16 hours of treatment time is all it takes to take sewage and turn it into near drinking water quality water. We currently meet state and federal guidelines for drinking water quality, and the reality is that 1 billion people on planet Earth would love to have this water to drink. It exceeds the quality and quantity of water they currently have access to. We ask people as they use water and send us water in the sewer to be conscious of two important things. One is water conservation. A drop saved is a drop that we don't have to clean. We don't have to go to the time and expense to clean that water and return it to the environment. And also that some chemicals are difficult to remove in our treatment process, so a discretionary use of cleaning products and personal care products is advisable not only for your own personal health, but for the health of the environment. Our treatment process today is mostly focused on the cleaning of water. Sewage is mostly water, over 99% by volume, but we do have 1% of solid material that we separate out mostly in step 1 in primary. And we're going to find out now what happens to those solids. We left them behind in the anaerobic digesters where they're being broken down over approximately 30 days and digested. Now we're headed over to our dewatering building and our hopper storage area, and we're going to find out what ultimately happens to those solids and how they leave this facility. All right, here we are at the dewatering building. Solids are going to come from the anaerobic digester after about 30 days digestion. They're going to be dewatered in this building and then loaded into this big hopper you see behind me. This allows us to fill the hopper up and then periodically through the day come in and load it up. So we fill on average 4 of those trailers a day, and the solid material then leaves the facility. Now it used to go 100% to landfill, to the dump. We were throwing away this solid material. But is it really waste? Now, waste implies something has no future value or reuse, and these solids certainly do not fall into that criteria. So the city of Santa Rosa didn't want to put all these solids into the landfill where they don't belong, so they started diverting solids away to a land application program. So we now take solids to agricultural fields where they can be spread and disked in, used just like fertilizer. So you can use chicken manure, you can use steer manure, hey, you can use biosolids. And of course there are restrictions because this is not pathogen free as it comes through the dewatering. We don't grow human food crops with it, we grow mostly hay. Well, the city wanted to diversify yet again to make even less solids go to the landfill. We now have a state-of-the-art compost facility across the street. So we take these biosolids and blend them with curbside green waste. That's our carbon bulking agent. And we have long beds that are mechanically agitated so the pile is evenly turned. And sensors in the bed wall allow us to continuously monitor temperature and moisture. And over 30 days of active composting, at the end, we allow the temperature to spike up to 150 degrees Fahrenheit for 3 consecutive days, and that removes all pathogens. And we now have what's considered a Class A product, which we can sell bulk on the market for unrestricted use. So you can put it on your fruit trees, your vegetable gardens, your rose bushes, whatever you want. We now take less than 1% of our solids to landfill, and they are almost all reused. So that's a nice direction the city of Santa Rosa has been trying to head, to think about ways of closing the loop. So this facility, this industry, is often referred to as wastewater. Now, I would argue there's no such thing as wastewater, that we have no water to waste. We need every drop of it. And so likewise with the solids, we have to think about reusing these natural resources and not wasting them.